Hello all, this is a session on linear algebra. We will start with understanding matrices and determinants. Okay, first let me see what do I mean by a matrix. What is matrix? A matrix is a two-dimensional structure. Okay, for basic understanding, and it is going to have rows and columns. It's going to have rows and columns, so it's going to look something like this: A, B, C, D. Okay, something like this. This is an example for a matrix. Clear? So a matrix is identified by number of rows and number of columns. The number of rows and number of columns identifies a matrix. That is, for example, if I call matrix A like this, this matrix A has two rows. Rows are nothing but horizontal. Correct? We know all these basics, right? Horizontal. That is, there are two horizontal things. These are rows. And two columns. Columns are nothing but vertical things. Correct? So it has two columns. Correct? And any entry in a matrix, I can represent it by a general notation called Aij. This is a general notation for any entry. General notation for an entry in the matrix, or an element in the element in matrix A. What do I mean? That is, I represents row, J represents column. That is, if A is a 2 cross 2 matrix, I can have A11, A12, A21, A22. So with reference to our example, what is A11? First row, first I reference to row, J refers to column. So with reference to our example, what is A11? Nothing but first row, first column entry. A12 is first row, second column entry. Second row, first column entry. Second row, second column entry. So if my matrix is a bigger structure, I can have A33, A44, A12, A13, A14, A15 like that. If the matrix is bigger according to the size, I can find these entries. Correct? So Aij is a general notation for a ith row, jth column entry of a matrix, or a ith row, jth column element of a matrix. Clear? And one important thing we need to understand: matrix, there is no restriction on a matrix. That is, it can be rectangular or it can be square. Square means what? Number of rows equal to number of columns. That is, our example itself is a square matrix. Correct? Two rows, two columns, both are equal, so it is our example is a square matrix. I can have a rectangular matrix in which number of rows is not equal to number of columns. Please pay attention to what I am writing here. I am not saying number of rows is less or greater. I am saying it is not equal to. That means I can have a matrix with 2 row 3 columns, 3 row 2 columns, 4 row 10 columns, 100 row 2 columns. Anything is possible. This is rows, this is columns. Anything like this is possible. All are matrices. This is a 2 cross. So a matrix is denoted like 2 cross 3 matrix. Means it is denoted as rows slash columns. That is the number of rows cross number of columns. Correct? So our example A is a 2 cross 2 matrix. So A here is a 2 cross 2 matrix. Okay? A is a 2 cross 2 matrix. Clear? Now let me see some types of matrices. And what do these types mean? All these types have a meaning which we will be seeing very shortly. So first thing I call something as a identity matrix. Okay, this is defined only for square matrices. Identity is defined, that is on all the entries. By the way, here the moment I introduce this, we will see many notations coming up. Okay, we will see also types and notations related to a matrix. So when I say it is a square matrix, I can associate a diagonal with it. Diagonal, that is, if I take a general purpose matrix, square matrix A, B, C, D, this line is a diagonal. It is called the leading diagonal. Okay, this is another diagonal, correct? These two lines are two diagonals, and this line in particular, this line where I am marking now, is called the leading diagonal. Okay, so in this case, this is the leading diagonal. This is the leading diagonal, correct? So a identity is a matrix. Identity is a square matrix in which all identity matrix is a square matrix in which all leading diagonal elements are 1 and all other elements are zeros. This is very important. Okay. So continuing, what did we saw? We saw that Aij is a representative of ith row, jth column element in a matrix. This we saw in the previous page, right? So if I have to define a diagonal matrix, how do I define? How can I define a diagonal matrix? A diagonal matrix is a, I'm sorry, identity matrix. How do I define an identity matrix? A identity matrix is a one in which Aij equal to 1 for I equal to j, and it is 0 else. Correct? Let us see this. Let us take a identity matrix. It should be always square, right? So let us take a 3 cross 3 identity. How it will look like? 1 0 0 0 1 0 0 0 1. Correct? This is how the matrix looks like. First row, first column is 1. Correct? Second row, second column is 1. Third row, third column is 1. Correct? So A11 equal to 1, A22 equal to 1, A33 equal to 1, A21 is 0, A12 is 0, A31 is 0, etc. So this is what I wrote here, right? If I equal to j, I represents the row, j represents the column. So if the row and column are same, I have a entry 1. If row and column are different, I have a 0 entry there. Correct? So that is what I have written here. So this represents a identity matrix. Aij equal to 1 for I equal to j. Aij equal to 0 else represents a identity matrix. This structure represents an identity matrix. This is another way of representing an identity matrix. Okay. Now here we understood what do we mean by in the process of defining an identity matrix, we understood what do we mean by a leading diagonal. Okay. Fine. There is another notation called trace. This is a notation Trace is nothing but sum of elements of leading diagonal. So the moment diagonal notation comes, it's whenever I refer to diagonal, it is always referring to a square matrix only, because I cannot define a diagonal with respect to a rectangular matrix. At the present moment, the conclusion is I cannot define a diagonal for a rectangular matrix. So sum of elements. So what is the trace of this matrix? What are the elements? This is 1, 1, 1. So 1 plus 1 plus 1 equal to 3. This is the trace for this matrix. Correct? So one important quick result what we can say, if I define a general purpose identity, M cross M identity, say if I define a M cross M identity, that is it is having M rows and M columns identity, what will be the trace of this? What will be trace of M cross M identity matrix? One quick result, it will be nothing but 1 plus 1 plus 1 plus 1 plus 1. How many times will be there? There will be totally M ones will be there. So this is nothing but M itself. This is one important property. These are all very important small conclusions. So trace of a M cross M identity matrix is M. Clear? These are very small definitions what we will make and small results which we collect and keep for our future understanding. Okay, fine. Okay, now second thing I want to introduce is a unit matrix. Okay, sorry. I want to introduce the notation of diagonal matrix to you. A diagonal matrix is nothing but its structure is such that it has non-zero entries in leading diagonal. Okay. Now I have to be very careful with these definitions because these are very tricky and all other elements are zeros. That is, if I take a 3 cross 3 diagonal matrix, I will have A, B, C. This is a 3 cross 3 diagonal matrix. So again what do we saw? The moment whenever I use the word diagonal, it is always with respect to a square matrix only. So diagonal matrix means internal. I am indirectly telling to you that the matrix what I am talking about is a square matrix. So now what is meant by a diagonal matrix? All non-diagonal entries are definitely zeros. All non-diagonal entries are definitely zeros. Correct? Some diagonal, the words I am using are really important, please pay attention. Some diagonal entries may be zeros, but not all of them are zeros. Correct? Means what? A, with reference to this example, A comma B comma C, all three cannot be zero. A itself may be 0, B can be 0, C can be 0, but A and B and C can never be 0. A is 0, B is 0, C is 0 means it will become all 0, 0, zeros. So that is not allowed. Few of A, B, C can be 0. Correct? Some diagonal entries may be 0, but not all of them are zeros. That is, A equal to B equal to C equal to 0 is not allowed. All the three cannot become 0 at a time for a diagonal matrix. Okay. Here I want to introduce the notation of row matrix and a column matrix. A row matrix is a one which is always having only one row. Which is always having only one row. Any number of columns it can have. For example, A, B, C. This is a 1 cross 3 matrix. A, B is there. It's a 1 cross 2 matrix. I have A, B, C, D, E. It's a 1 cross 5 matrix. So, by generalizing, row matrix will be of the form 1 cross m, where 1 is the row, m number of columns are there, and m is a natural number. Remember that. M is a natural number. Okay, m cannot be a int. For example, m cannot be a fraction. I cannot have one row and 3.5 columns or 3.7 columns. So m is a element of natural number. Clear? M is a element of natural number. So this is how a row matrix will look like. A column matrix, how it will look like? A column matrix will always look like it will have one column and any number of rows. So A, B, what it is? It is a 2 rows, 1 column. Correct? A, B, C, D. It will look like this. This is having 4 rows, 1 column. How does this look? A, B, C, D, E, F. This is 6 cross 1. So by generalizing, what can I write? By generalizing, a column matrix will be of the form m cross 1, where m is the number of rows. This is column. Correct? And m is an element of, m is a natural number. That is, in the number of rows are natural number means what? It can be 1, 2, 3, 4 like that only. It cannot be 1.2, 1.7 like that. Correct? I cannot have a 1.7 row cross 1 column. Correct? So this is what is a row matrix and a column matrix. Now let us understand something called a symmetric matrix. What do I mean by a symmetric matrix? For understanding this, I need to understand an operation called transpose. What do I mean by a transpose of a matrix? I need to understand this. Suppose if A is transpose is an operation in which rows and columns of a matrix are interchanged. That is, suppose if A is a matrix written like this, A, B, C, D, what it will become? I write the rows as rows and columns are interchanged. So rows will become columns, columns will become row. So AC was a column, that will become a row here. It was the first column, it will become the first row here. AC. Second column will become the second row. That is BD. So this is nothing but A transpose. I denote it by A transpose, A superscript T. So this is what is the transpose operation means. Okay. Now, how can I write this transpose operation? This is nothing but Aij will denote A. All the collection of Aij is denoting A. So what will be A transpose? A transpose will be nothing but Aji, right? So ith row, jth column will become J. See, you see here. First row, first column is first row, first column here also after taking transpose also. First row, second column entry became second row, first column entry. Correct? That is, First row, second column, A12 upon taking transpose became A21, correct? This is what is a transpose operation. So A transpose means it Aij will become Aji. All the entries are swapped. The rows and columns are interchanged like this. Correct. Now let us see what is a symmetric matrix. If A is a matrix such that A transpose is equal to A, then it's called symmetric. Okay. That means what? After taking transpose also, it is same. So let us observe, let us make few important observations here. Observe. If I take a transpose, so let me take this. If 3, 4, there is a matrix like this. Let me call this as A. Then what is A transpose? A transpose is I have to write the columns as rows. So first row, this is having 2 columns, 1 row. Correct? So first row, first column entry will become first row, first column entry here also. Now the rows are replaced by columns. So A transpose will have 2 column 1 row is the number of entries in A. So A transpose will have 2 rows and 1 column. Upon taking transpose, it will look like this. Correct. So if I take a transpose, of a m, if A is m comma n, A transpose will become n cross m. Correct. If A is a m row n column matrix, A transpose will be n row m column matrix. This is the first observation. Okay. Now let us go for the second observation. Let us make few more observations here. Okay. Let us see. What do I mean by symmetric matrix? A transpose equal to A. Then I say A as symmetric matrix. Correct. This is what I mean by a symmetric. Now what was the last result we saw? If A is a m cross n matrix, A transpose will be an n cross m matrix. Clearly m cross n can never be equal to n cross m. Correct? Only if A is m cross m, A transpose will also be m cross m. Even then these two need not be same. Even if this is satisfied, even then A need not be equal to A transpose. Why? Let us take an example. See, this is what I am trying to prove here is if A is m cross n, definitely A cannot be a symmetric matrix. Whereas if A is m comma m, then there is a chance. Say for example, if I say A is equal to 1, 2, 3, 4. What is A transpose? It will be 1, 3, 2, 4. So A and A transpose are not equal. But if I say A is equal to 1, 2, 2, 1. What will be A transpose? A transpose will again be 1, 2, 2, 1. Correct? These are equal. Correct? So, what does that mean? Even if the number of rows, even if A is a square matrix, A need not be equal to A transpose, but there is a chance. But if A is a rectangular matrix as discussed here, there is no chance of symmetricity. Correct? No chance of symmetric. Therefore, if A has to be symmetric, A must be a square matrix. This is another important observation. Please remember, these are very small observations which we are making, which will be very useful in the future. Then we will discuss something called triangular matrix. If I have a matrix like this, or I can say I have a matrix like this. Here I see that in these two cases, please observe, let me call this as A, let me call this as B. I observe that here all the elements above the diagonal is 0. Here all the elements below the diagonal is 0. Correct? Yes or no? So, this type of structure is called upper triangular matrix. This type of structure is called lower triangular matrix. Please remember that. This is called an upper triangular matrix. This type of structure is called a lower triangular matrix. We will see these matrices are defined with some intention, which we will be visiting shortly, and we will be understanding the intention of defining these type of matrices very shortly. Then proceeding ahead, we will be seeing some operations associated with matrices. First thing we will see is scalar multiplication. That is, I have a matrix called A which looks like this. I am taking an example of a 2 cross 2. Then how will Ka look? K is a scalar. Scalar means it's a what? K is a real number. K is a real number. It's a real number. K is a real number. So mathematically I write it as K is a element of R. R means real number. K is an element of real number. Like this I can write it mathematically. Then how will the matrix Ka look? It will look like Ka, Kb, Kc, Kd. This is what it will look like. So what does this mean? If I multiply a matrix by a scalar, every entry here is multiplied by that K. Correct? So if I have to write Aij, A is equal to Aij, then Ka is nothing but Kaij. Every entry is multiplied by Ij. Here there is no need for square, no need that A must be square. Please remember this. There is no restriction. Second thing we will see is matrix multiplication. This is very important. We will establish some few important relations here. So let me take a matrix called A, let me take a matrix called B. The matrix multiplication operation is defined like this. Rows of A gets multiplied with columns in B. That is, say for example, if A looks like A, B, C, A1, B1, C1, D1, and B looks like A2, B2, C2, D2. Now how will be AB? AB will look like the row and the column, it will look like A1 A2 plus B1 C2. Then again first row with the second column I need to multiply. That will be A1 B2 plus B1 D2. Then the rows are multiplied with the columns. Correct? C1 A2 plus D1 C2. Here I will get C1 B2 plus D1 D2. This is how AB will look. Okay. This is just for example sake we did. Now let us explore this further. Say for example A is equal to A, B, C, D. B is equal to E, F. What is A here? A is a 2 cross 2 matrix. B is a, how many rows are there? 2 row, 1 column is there. How will AB look like? I fix the row, I fix the column. Rows get multiplied with columns. So AE plus BF I will get. Then I will get CE plus DF I will get. Correct? I will get CE plus DF. So what do I get here? I get, what is AB here? What is AB here? Here AB is a 2 cross 2 matrix. Here AB is a 2 cross 1 matrix. Okay. Now let me take A is equal to A, B, C, D, and let me take my B as E, F. What is A here? It's a 2 cross 2 matrix. B is a 1 cross 2 matrix. Now what will be AB? AB is what? I need to fix a row. The rows get multiplied with the columns. That means I have to multiply this with this. This is not possible. Why? Because I don't find, I will multiply A with E, but with B what will I multiply? Here there is no entry here. There is no entry here. How do I multiply? With what do I multiply B? There is no entry at all. Correct? So why this happened? Because here I have 2 columns, 2 row, 2 columns. I multiply the rows with columns. That means the number of columns here and the number of rows here are different. They are not same. See here I was able to multiply here this and A and B here because A is a 2 cross 2 matrix, B is a 2 cross 2 matrix. If I have to multiply the rows with column, this columns and rows were matching. Similarly, A was a 2 cross 2, B was a 2 cross 1 matrix, but still the number of rows in the second matrix matched the number of columns in the first matrix. So it is possible to multiply. Correct? So if I generalize, if I have to multiply A and B, AB is possible. Say, let me say that A is say some M cross N and say B is some P cross Q matrix. AB is possible if and only if N equal to P, or else it is not possible. Clear? This will not be possible. And what will be the result? Assume that this is possible, then what will be the result? Then how will be the result? Rather, how will be the result? Rather, the structure of the result, how it will be? See, I multiplied a 2 cross 2 with a 2 cross 1. I got it as 2 cross 1. Correct? So basically, what does that mean? If I have to multiply a M cross N, I need definitely some N cross P matrix. This N and N should be equal. This is the condition which we saw here. The result will be M cross P. The result will be of the structure M cross P. Please remember this. Now having said that, if I have to do a matrix multiplication AB, A is of a form M cross N that poses an immediate constraint on B such that it should be of the form some N cross P, and AB will be of the form M cross P. Correct. Now, is AB equal to BA? The answer is no. Because A is M cross N, B is N cross P. So, this condition was met and the result was M cross P. This was the result. If I want to do BA, what will happen? I will have a N cross P and A will be M cross N. These two are not equal. So BA does not exist. So hence AB is not equal to BA. Please remember this. This is very important. This is very, very important for with respect to a matrix manipulation. AB need not be equal to BA. This is not always true. Rather, if I write in English, AB need not be equal to BA. That is, it may be equal or it may not be equal. Say for example, A is a 2 cross 2 matrix. Say A is a 2 cross 2, B is 2 cross 2. Then AB is also possible, BA is also possible. Correct? So there are specific cases in which AB equal to BA is also true, but on a general notion, AB need not be equal to BA in case of a matrix multiplication. Please remember this. Okay. Next important property what we will like to see is inverse of a matrix. If I have a matrix called A, the inverse is defined as A inverse equal to 1 by A adjugate of A. This is what is A inverse definition. Now, if I have to find A inverse, I need to understand this, what does this mean, and I need to understand what does this mean. And the property of inverse is such that A into A inverse is same as A inverse into A is same as identity. This is very important property we need to remember. Inverse, when I multiply the matrix with an inverse, it's same as the identity. And also A inverse, what is this? This is the inverse of A inverse. Correct? And it so happens that A inverse is A itself. How? Can you prove this? Yes, we can. How? A inverse dot A inverse should be equal to I. Correct? Also we know that A inverse into A equal to I. So by comparing these two, let me call this as 1, let me call this as 2. By comparing 1 and 2, A inverse is nothing but A. This is again a very important result. So we have established so many results using A inverse. But We need to find how to calculate A inverse, that is given by this formula. This is the formula to calculate A inverse. But I don't know, till now I have not seen what do I mean by adjugate of A and this. This is what we are going to see further going ahead.